structures anymore. Oh, I guess I should say. Okay, good morning. So, I don't know why I put the book down because I'm going to need that today. Today, we're going to be doing something similar to what we've... Good morning, indeed. What we've done similar to Thursday last week, yeah. So remember we used Hess's law to kind of manipulate equations that we did know delta H for to figure out the delta H of an overall reaction. That's what we did last time. We're going to be using a special type of reaction called a formation reaction today to help us out, because these are also very well tabulated in chemistry, and so it's easy for us to kind of just piece together bits of already known reactions to try and calculate the delta H for a total reaction. Alrighty, so let's see. Let's go ahead and take a look at it. First things first, we have what are called standard enthalpy of formation. That is abbreviated like this, because why not? We can just have delta H with a cajillion things on it. Let's see if... yes, this will work. Okay, so notice if we go to our fancy table, we see that, in fact, this delta HF with a little, not a degree symbol, it's kind of a degree symbol, it's called naught, is what's given to us on this table. And so this table is actually going to be the formation of whatever this product is, based on the reaction that produces 1 mole of it at these two conditions. So this is the delta H for a reaction that produces 1 mole of product from elements at 25 Celsius and 1 atmosphere. You can't see it. Oh, very good. Yes. I thought I would just show you this giant table the whole day. So, sorry about that. I'll give you all a second. Okay, so fancy delta HF naught standard. We're going to see that this little this little dude up here, do not need you to translate into English, is means standard conditions. And that's usually 25 degrees Celsius and 1 atmosphere. And so, I have this one written somewhere. delta H was negative 393.5 kilojoules, right? Notice that this is, if this reaction takes place at standard conditions, then the heat of formation is going to be the heat of reaction, because we're just using elements to put them together to make a compound. Notice that we have the coefficient of 1 for our product, and we're going to see that that's going to be something that we're going to have to do for all of our delta HF at standard conditions. So this one would be an example of an enthalpy of formation, because it's taking elements, individual elements, carbon plus oxygen, putting them together to make 1 mole of carbon dioxide. And if we're doing it at 25 degrees Celsius and 1 atmosphere, our heat of formation will equal our heat of reaction. All right. So we can use this this idea of heats of formation to help us out here. With multiple reactions, just like before, the sum if we are going to have more than one reaction, if we add up our heats of formation, we can get the heat for the overall reaction. Oh man, that's so annoying. My tablet is like half on my desk. Individual reactions, and this guy would be the overall reaction. Okay, so let's go ahead and take a look at an example. So this one is example, doesn't really have a number, but that's okay. We're going to calculate the enthalpy for this reaction. I have it balanced already, so we'll be okay. So if we want to take a look at these, if this is our overall reaction, the question is, what's the delta H for this reaction? We can find out by and of course we're going to assume this is at 25 degrees and 1 atmosphere. What we can do is find the delta HF for each compound. So what we're looking at here is our fancy table again. We can look up all of these. Oh my gosh, this is going to be so confusing. Okay, there we go. Let's look at all the products we have in our each compound rather we have in our reaction. So looking at this, we have carbon dioxide. That's one of them. We know that this is the reaction that will give us carbon dioxide. Delta H is negative 393.5 kilojoules. So that's one of the compounds. I'm just doing it in kind of a whatever order I see them. This is another compound for our reaction, the propane. This reaction, it looks like, will have a delta H of negative 103.9 kilojoules. By the way, if you're wondering, again, you can't see it. Oh, well, okay. We'll see it in a second. Let's look up water now. That's our last one. Water. Where's oxygen at? Aha! Heat of formation of water is negative 241.8. I'm just going to write that here. Delta H equals negative 241.8. Okay. Kilojoules. Okay, sorry. I'm so sorry that I keep forgetting that this table blocks everything. So, here, I'll get rid of these so we can all do it together. If we take a look at these three numbers we've gotten from that big old table, we looked up carbon dioxide, propane, and water. And if we want to find the reaction that would produce these delta HFs are always from the elements themselves. So we look at each compound and see what elements is it made of, and we will make an equation accordingly. So the elements that make up CO2 would be carbon plus oxygen. Remember, we always indicate whatever state it is at 25 degrees Celsius, that's room temperature. So at room temperature, carbon is going to be a solid, particularly in graphite form, and oxygen is a gas, that is O2. We put them together, we have a particular delta H for that. For the next one, we have again carbon plus hydrogen now gives us propane. We have a little bit of balancing to do. Remember, we always use the elemental forms of these guys. And the last one. Again, we're just using the elements themselves to make this. And remember that we always need to have a coefficient of 1 for our product if we're going to use delta HF. And so that tells us we need to have this silly 1/2 there. So technically you would, if you were being a good chemist, you would say 2H2 plus O2 turns into 2H2O. But for a delta HF, we must have a coefficient of 1 for the product. And there's always just one product. So that's how these are given. So as a result, we're going to have 1/2 for our oxygen there. Okay, so this is essentially, we're doing the same thing as before, except we are going to be essentially just looking up information from a table as well as coming up with reactions on our own. So last week we were given the reactions that we would use to kind of put together to find the total delta H. In this case now we're looking up our own reactions. So that's the only difference here. So let's go ahead and look at our overall reaction. Can you hear Oz like puking and dying out of curiosity? Just, it's a nice unsettling sound. Yeah, that's, he just has, so old small dogs often just have tracheal collapse. That's when they're, they just have weak cartilage, so their throats kind of close a little bit, so they make the sound as though they're like dying and puking just to open their throats up again. And it's totally like harmless, but it just sounds horrible. So it's kind of like a cat with a fur ball, right? So same idea. Okay, so let's go ahead, and I realize these are all in the same color and it's going to be a total mess. Here's reaction 1, reaction 2, reaction 3. It doesn't matter what order or which one is number one. As we know, we're going to add them up anyway. So we want to see here what we have to do to make it such that this reaction will, just like the Hess's law stuff, we have to make sure our products are on the product side and we have the right coefficients. So if we look at that first reaction, what we're looking to get out is CO2, right? That's part of our overall reaction. So we have to think about CO2 here. Okay, it looks like we have 3 CO2s in our overall reaction. So we're going to need to multiply this one by 3 when we add up our delta H's. Everyone see why that is? We'll need 3 of those to make sure that we produce. Okay, and look, Kevin's already gone ahead. Yes, and so we see that here propane is a product on the other one, so we will reverse this one. And then the last one, we will need to multiply by 4. One thing to note also, I might have not explicitly said this. This oxygen here is already in elemental form, so its delta HF is 0. Delta HF for formation of an element is always 0, so we don't have to worry about that. So we can omit it from the calculation. All right, it's only compounds that we're looking at. Okay, and so if we do that, it looks like we had to do times 3 and then reverse and then times 4. So the total delta H reaction for this is going to be 3 times delta H1 plus negative delta H2 plus 4 times delta H for reaction 3. Again, I'm just copying. Remember, reversing means we flip the sign, just negative. So we can put all these together. And so that's going to be 3 times negative 393.5 kilojoules plus 103.9. And 4 will be negative 241.8 kilojoules. And thank God Kevin has done it all for us. He has figured out this will be our thing. Technically with sig figs, we're okay. We're good. Perfect. All right, I'm promoting Kevin to your new teacher, okay? So I'm just going to go on vacation or something, and he's just going to teach the class. Very nice, very nice. So the delta H for this reaction will be 2,043.8 kilojoules. And of course, this is exothermic, right? It's a combustion reaction, so we're expecting it to be. And let's see if we got it right. So this thing looks like, oh, because they use water as a liquid. Oh, whatever, who cares? I put it as a gas, we're okay. Okay, questions on this one? We have more we can do. Uh-huh. Oh, we should have done water as a liquid because it's liquid at room temperature. Oh well, forget it. We're okay. I did it as a gas. It's a different reaction. We're cool. Okay, anyways. Another one. Combustion of benzene. Producing liquid water this time because I should have done that before, but that's okay. And carbon dioxide. So this could be a totally valid problem. What's the delta H of reaction for combustion of this benzene? So first things first, of course, the question, by the way, will tell you if water, where did the plus 4 come from? We needed to multiply our last reaction by 4 because we had 4 waters in our total reaction, so we needed to multiply the third reaction there by 4. And that would give us 4 waters. Okay? Let's go ahead and balance this. Hopefully the book has done it. Yes, good. Oops, these are reversed. Oh, by the way, this one is actually from the book, so this is exercise 5.12. In the book. Okay, cool. So let's put our state symbols in there. This one is telling us we're producing liquid water. So this time we're going to use delta H for liquid water. Okay, so again, looking at these compounds, we're going to have to look at what's going to make benzene and look up its delta HF. A second compound we have is liquid water. So we're going to make liquid water and find its delta HF. And the last one is carbon dioxide gas, which we already have probably memorized by now because combustion is so common. Negative 393.5 kilojoules. Again, this table, the table that I've put up for you is it's part of your homework. I've put it in the description for your homework, and it's also in Discord in our extra resources area, if we need that. Okay, so before we look up our delta HFs, let's go ahead and write our reactions. And so this one again is going to be, we've already done. Same thing here. And so the last one is the only one, or rather the first one is the only one we haven't already done. So let's work on that. So that's going to be 6 carbons, right? Plus 3 hydrogen gases coming together. And so those are the reactions we're going to need here. Okay, let's look up our delta HFs. So back to the table. Alrighty, here is liquid water written for us. It is negative 285.8. And if we're going to have to look up benzene now. So we're going to scroll all the way up. We're going to find carbon. Here's carbon. We find C6H6 liquid. Tells us it's 49.0 kilojoules. Yes, great. Okay, cool. Back to this. So all I've done is plug in the numbers that we got from the table. And so just like before, we are going to now take a look at our reactions and see what we need to do to make them work. Alrighty, so looking at benzene here compared to our the combined equation versus the first one, looks like we're going to need to reverse this. Because we want benzene to be a reactant. Oxygen we're going to ignore. So because it's an element already, delta H of 0. So water looks like it needs to be a product, and we need 3 of them. So multiply this by 3. Carbon dioxide looks like we have 6 of those. So we'll need 6 of that reaction. And so the total delta H should be, delta H for this combustion reaction should be the reverse of the first one, so negative delta H1 plus 3 times delta H2 plus 6 times delta H3, which is going to be negative 49 plus 3 times negative 285.8 plus here we go, 6 times negative 393.5 kilojoules. Thank you, Kevin. Wow, that's quite a lot. Makes sense, though. Okay, so that's negative 3267.4 kilojoules. And remember, these are technically per mole, right? Like that's essentially what a delta H reaction is. It talks about the moles, right? And so that would be the best way to describe it. Cool. So how are we feeling about these? Shall we do another one? It was already positive. Okay, yeah, we'll do another one. So, erasing that. Okay, yeah, it was positive to begin with. I know. It sucks. It's just a screen of black writing of, the thousands of equations. So totally. Okay, let's see. Shall we do one from your homework? Or no, let's do, oh, here we go. Here we go. No, forget it. Okay, let's see. Let's not do one from the book. I want to do one that's, maybe I should, oh, whatever, let's just do one that I want to do. Okay, let's say, let's do something special. Okay, let's take peroxide now to do this reaction. Oh gosh, I'm gonna have to balance this, aren't I? Oh, how annoying. Okay, well, it's good practice, right? See, look at this. I tried to be creative and do my own problems, but now look at how much work it's going to be for everyone. Okay, let's see if we can balance this. So, 6 carbon dioxides. So, let's see if... So we're going to need at least 6 of those guys. But we're actually going to need 9 of them. If I remember this correctly. It'll be 18 plus 9. Yeah. Is that right? 9 oxygens plus 12 oxygens. This can't be right. Oh, balancing is so hard. Okay, here. We'll do this systematically. This one I cannot do in my head. Alrighty. So we have 6 on the left, 6 on the right. We have, oh, because, duh, we have hydrogens there. Okay. So there's your pro tip for the day. Being a chemistry instructor does not mean you can balance equations in your head automatically. And so we have 12 plus 1 is 13. That's already annoying, but we can deal with that. So let's go ahead and make this so it's 26. So let's make 13 here. If that's 13, oh gosh. Okay, I'm going to do this balancing a separate way. Look at how committed I am to this problem. All right, don't look at this. This is another way to balance equations that I'm not going to teach you. So just give me a second. You have 6a plus 2b equals 2d. And so in the meantime, type up your questions for thermochemistry while I have foolishly decided to make my own problem that's making everything much more difficult for us. Isn't this exciting? Oops, that's a C. C plus D. Okay, that's good. What can we substitute here? Okay. Equals 12a. Plus 3a plus b plus 3b equals 15a equals 3. Okay, cool. And then C is 18. Okay, so doing this horrible reaction, we're going to get 3 benzenes plus 15 hydrogen peroxides turns into 18 carbon dioxide, and D is going to be 30 equals 36 plus, no, that can't be right. What was B? 15. C is 6 times A. Oh, it's O. Why is this so hard for me? D equals 3A plus 2B. That's right. So let's see. Why can't I think of this? 9 plus, what did I say B was? 15, which is 24. Okay. Hey, look, doing my way, I need to fix this still. How utterly annoying. They can all be divisible by 5 or 3. Did anybody have any questions? Yeah, advanced balancing, right? Okay. See, that wasn't so hard. Okay, now we can actually do this. See, shame on me for trying to give you one that's going to have 4 reactions. Okay. So ignore the advanced balancing, and now we can do this thing. How annoying. Okay, cool. Let's do it. So this time we have 4 compounds, so we're going to need 4 equations. Equation 1, 2, 3, and 4. With the benzene, it's going to be same one from before. That one happened to be 49, positive 49. I will put a plus so Tyler does not get confused. Awesome. Second one is now peroxide. So what do you think the equation is going to be for peroxide? While I get the rest of this going. oops. I want you guys to write the equation for formation of peroxide, hydrogen peroxide, I should say. Remember, we always, yes. Oh, that is easy. Never mind. There are no crazy fractions in this one. I'm trying to trick you. It's not working. There's both gases. Delta H for this one, negative 393.5. Last one was water, right? Okay, and so, technically you don't need to write out all these equations. Technically. I shouldn't say anymore. It'll give you too many secrets. Technically, all you need to do is look up your delta H's and use your reaction coefficients and negative them as necessary. But it's always a good idea to do real reactions. Okay. This one we have before was 285.8. So let's look up peroxide on our chart. Peroxide is oxygen-based. Hydrogen peroxide, I'm sorry, I just keep calling it peroxide. H2O2. Here it is as a gas. Do we have it as a liquid? Oh, thank goodness. Okay, we do. And so that's now negative 187.8. By the way, these don't have to be combustion reactions. We could do this for any reaction. But just combustion is the most common. So, but yeah, we can do it for anything. Okay, cool. Let's have a look. So, what do we need to do for these four reactions? What do we got to do here? First one, of course, we'll have to reverse. Second one will need to be reversed as well, right? Because it's also a reactant. And we also have to multiply it by 5, right? Because we have 5 peroxides, hydrogen peroxides, sorry, in our reaction. And so next one, we're going to have times 6. Last one times 8. So delta H for the total reaction is going to be negative delta H1 plus negative 5 times delta H2 plus 6 times delta H3 plus 8 times delta H4. So negative 49 minus, actually that one's going to be plus, isn't it? 5 times 187.8. I'm going to just keep that as minus, just so it's easier for us to follow. But I'm sure Kevin has already calculated it, but that's okay. I've run out of space. Next one we'll do, we won't do a combustion reaction. We're going to do one that's easy, just a non-combustion, just so I can show you it's not always the same thing. There are slight things we might have to do. Great. So negative 3757.4 kilojoules per mole. Woo! Exciting. Any questions on that one? Ignoring the whole 5 minutes I spent trying to balance that stupid equation, which turned out to actually not be so hard, apparently. Coefficients turned out pretty nice. Maybe there's one in the book that I can use, so I don't have to deal with that. No, that's boring. Maybe we'll do one from your... No, this is boring as well. Any questions on this one? I don't want to do your homework for you. These are boring. Did I give you guys number 76? Fine, let's just do number 76. Okay, so this one says that calcium carbide is reacting with liquid water. Why was H2O2 reversed? Because it's a reactant. Because this guy is a reactant. Remember, the whole point of doing these things is to make it so that we add up all the equations and we should get our overall reaction. So technically what we want to do is make it H2O2 turns into H2 plus O2. And by doing that, we have to make our delta H into a positive number instead. And since we also have 5 H2O2s, we have to make it so that our overall reaction is 5H2O2 turns into 5H2 plus 5O2 for a total delta H of 5 times 187.8. So the short answer, it's because it's a reactant. So reactants you're always going to have to reverse. Oops, we do not need to happy green. Calcium hydroxide. Yes. Acetylene gas. And so this problem is telling us that delta H reaction is negative 127.2 kilojoules per mole calcium carbide. And this time it's asking us to find the delta H of formation for calcium carbide. Exciting. So we would approach this very much the same way as before. We would want to come up with our equations that we need, right? Is it okay if I don't write out every single reaction this time? Is that going to make anyone sad? So just remembering that delta H is always don't forget this. You know what? Let me not even worry about this. If we think about it, we have 4 compounds here, right? If we think about this, we're going to just need negative delta H1 minus 2 times delta H2 plus delta H3 plus delta H4. So this reaction is already balanced. We just need to remember that for the first 2, since they're reactants, we're going to have to make them negative. So reverse them. I shouldn't say make it negative. We reverse the reactions. And so this question is asking us essentially to calculate delta H1. So we know this thing has already told us that our delta H reaction for 1 mole of calcium carbide is given. We do not know the delta H1, that's what we're looking for. And so we would just look up the other ones on our table. So we have liquid water, which is negative 285.8. Sorry, my parentheses are rather awful there. Next one we have is calcium hydroxide. So we'll go up to calcium hydroxide. Calcium, where are you? Here we are. Calcium hydroxide tells us it's negative 986.2. And delta H4 was C2H2. So that's carbon. That's acetylene gas. Is positive 226.7. 226.7. These are all kilojoules, so I'm just going to omit the units. I hope that's okay. And so all we have to do is solve for delta H1, which I'm sure Kevin has already done. But so delta H1 will equal 127.2 plus, Kevin, please do it. I don't want to do this. I don't like calculating. 2 times. I mean, this is algebra. You guys can do this part, right? 571.6 minus 986.2 plus 226.7. Oh my goodness, we might actually have an endothermic reaction. Maybe. Oh. No such luck. Whoa, what happened here? Did I do something incorrectly, Kevin? Did I calculate this wrong? Oh, we may have beaten Kevin. Double check, Kevin, because it is always possible that we've gotten it wrong too. So double check yours, see if you get negative 60.7. So unfortunately, this is still exothermic. I wanted us to get an endothermic one eventually, but lo and behold, we did not get so lucky. Alrighty, so there's kind of our first shortcut there. We saw that we did not need to necessarily write out all the reactions. As long as we use the coefficients and where they are in the reaction, we'll be okay. That's how we can sum this up. So we do not necessarily need to write out our reactions. All right, so while Kevin's checking on that, we can also look at it this way. So remember, delta in chemistry always is final minus initial. Another way of writing that is products minus reactants, right? The final thing minus the initial thing. Hooray! Okay, so we have overruled Kevin. Kevin, you are no longer the chemistry instructor. I guess I'm going to have to actually do my job, so damn. Oh well. And so, for a reaction with here's a random reaction. This equation, or formula rather, since you people love formulas, I do too. It'll make it easy for us. Is we can separate it like this. As long as we understand that we have with coefficients, I'm just going to write that. So, for example, if you had 2 for C, you would use 2 times delta HC, right? This is one way to kind of compartmentalize what we've done. Awesome. I'm glad Kevin got it. So we're going to see that before, we ended up doing the same thing. We just had it in a slightly different order. So notice that these guys were negative, right? Because those were our reactants. And so that is the same as this part here. So that's why they were negative in our kind of formula. So this may help you to do these much more quickly for ones that involve delta HF. Cool. You might see in the future what are called enthalpy diagrams. If we take this particular reaction, this calcium carbide plus blah, 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 doing all this stuff, we can see what's actually happening here. So here are our reactants. We are experiencing a delta H reaction of negative 172, 127.2 kilojoules. And that's turning into the products, right? Which were calcium hydroxide and water. Or CO, what was it, CO2? No, acetylene. What this is telling us is, where are our delta H's? Here they are. We're going to see that putting these all into kind of context, we can break them all into their elements and then put them together step by step. So we can say that the formation of water, I'm sorry I keep scrolling everywhere, I'm just trying to find our numbers, was negative 285.8. Right, so just trying to diagram this for you guys because you'll see these a lot. And I don't know why I've chosen such a complex reaction to diagram for you guys, but lo and behold, there it is. So we know that going from water, that's H2, oh my gosh, H2 plus half O2, right? We know that this difference was negative 285.2. We're just showing different energy levels. So what we're going to be able to see is that we can use this kind of Hess's law idea to just go bouncing around between things. So we have our calcium and hydroxide. Oh god, this is so complicated. Why did I choose this one? Okay, forget it. We're going to use a different reaction because this is just absurd. I keep choosing complicated reactions to do these for. Here, let's do it for one of the easier ones where I have the numbers like right here as well. I'm sorry, everyone. I tried to make this so nice for us, but good intentions, right? Aha! Okay. Here's one. We'll do our propane example, because thankfully this one is in the book, so I don't have to actually look anything up. So our overall reaction was C3H8 plus 5O2, right? That was our reactants, and we saw that we produced 3CO2 plus 4H2O. And we saw that this energy difference, which was delta H reaction, what we calculated to be negative 22, I forget. What did we calculate this to be? Who cares? We'll figure that out later. Just to describe to you. What we could also do is we can break these compounds down into their elements, which was 3 carbons plus 4 hydrogens plus 5 oxygens. And so that was delta HF of C3H8. And we saw that we could combine what am I saying? Carbon dioxide, right? We could combine these guys into carbon dioxide. How many oxygens do we have left? 2. And then we can go back to this level where we have our, actually it's going to be just the same thing. So this is essentially what we're doing if you want to think about it visually. So this is delta HF of CO2 and delta HF of H2O. And so notice that we had to flip the arrow for breaking this guy down, because this is a reactant, right? Notice for oxygen, nobody cares. So this is essentially the pathway we're going to figure out this delta H reaction. And so that is technically, delta H reaction is delta HF of the water plus the delta HF of CO2 minus the delta HF of propane. And technically we have some coefficients here. We had 4 waters and 3 CO2s, right? Just visually displaying what we're doing here. So we have to essentially break apart our thing into its elements. Remember that the delta HF of propane was negative, but since it's a reactant, we have to flip it. It's going to actually cost us energy to break that apart. And so we're just kind of looking step by step what we're actually doing with this delta HF nonsense. I know that this is probably like, what the hell's the point? Who cares? This is something you just might see. I'm not going to give it to you on an exam or anything, but visually this is what's happening here. So we're using these delta HFs of all these steps to illustrate that the energy difference being a state function is just the combination of them. So visually we are going in terms of energy. If this was a graph, at each step we start with a certain amount of energy in our reactants. We have to essentially kind of add energy to break it into elements, and then we can combine those elements together, releasing energy to get our overall reaction. Okay, so again, I understand it's not really that exciting or necessary for you guys to duplicate this if you have to, but this is essentially what we're saying here. Okay, with that, we are done with thermochem. Hooray! There is technically one more section in the book which is about like carbohydrates and fats and stuff. We're not going to do that. So we don't have to worry about that sort of thing. So with this, you will all be able to do your homework. In my dictatorship of power, I have decided that we are going to make this homework due on Saturday, so that I can upload the answer key for you guys, so that you can double check your stuff on Sunday before your exam on Monday. Your exam on Monday is only covering solution chemistry and thermochemistry. So the stuff that we start learning tomorrow and Wednesday is not going to be on your exam. Thursday, we are going to do a review. So you are going to bring me questions for Thursday. They could be homework questions. They could be just, hey, could we do one more example of this sort of thing? Or, hey, I'm just confused about this concept of heat and exothermic versus endothermic, whatever. I'm happy to answer that sort of stuff. So I'm not going to cover new material on Thursday. It'll just be going over stuff again or clarifying things or doing more examples. I'm not going to do your entire homework. So if everybody's like, hey, can you do 71 and can you do 72 and 73 and 74 and 75? I'm not going to do all of those. But I would be happy to find other examples. I have other textbooks lying around that will have good examples that I can draw from that will have everything nice and neat so I don't have to spend 20 minutes balancing equations on Thursday. So, yeah. So with that, we're good. I will see you guys tomorrow. Have fun. You can do all your thermochemistry homework tomorrow. Potentially, I believe it will have the same time limit, but of course it's not going to have as many questions, right? Because these are more calculation intense. So, yeah. But, if you have questions about the exam in general, of course, throw them in Discord. We'll see how that's going to work out. Okay? Very good. See you all next time.